Nuclear chemistry. Nuclear chemistry has to do with radioactivity, where it has to do with the spontaneous decomposition of atoms to form different nuclei and producing particles and energy. Radioactive atoms are heavy and unstable, so they decay into an atom that's a little bit more stable. Example would be uranium. Uranium is a very unstable isotope, and what it does is it decays to form isotopes that are more stable. But in the process of decaying, it lets off particles as well as energy, and that's what we call radiation. When you take a look at nuclear equations, you have to take a look at all the quantities that are conserved. Okay? So what quantities are conserved? Mass and charge are conserved in nuclear equations on both sides of the equation. Okay? A stands for the mass number, so the number of protons and neutrons, and Z stands for the atomic number, protons or only electrons. There's 5 types of radioactive decay. One type is called the alpha particle, and what it is the release of just a helium nuclei. Okay? So here's an example. We have Ra22, and it decays by releasing an alpha particle. So here's my alpha particle right here. Okay? And it turns into Rn218. Notice how 218 plus 4 gives me 22, and 2 plus 86 gives me 88. Okay? Notice how we're using the law of conservation of mass. The next one is called a beta particle, and what it is a net effect of changing a neutron into a proton. Here's an example. Here's my beta particle, and notice how what's happening is that the proton is turning into a neutron, but the mass number still stays the same. Okay, so we start off with 91 protons. We start off with 90 protons, and we end up with 91. Okay, because we're changing a neutron into a proton. Okay, next we have positron production and the net effect of changing a proton to a neutron. So it's the exact reverse. Okay, so we start off with 11 protons here. We end up with 10. Okay, and this again changes from sodium to neon, and here is my positron production. Okay, that's my positron particle. Electron capture is where one electron is captured by a nucleus, and it looks like this. Here's my electron. Kind of looks like a beta particle, but in electron capture, the electron is on the reactant side, whereas in the beta particle, it's on the product side. Okay? And again, all these numbers need to add up together. Okay? And that's what you're looking for. Final one is called the gamma ray, and it's basically a high energy photon of light. And it looks like this. Here's my gamma ray. It doesn't have any mass, so we're not going to worry about that. But here's an electron capture right here. Okay, so this example has 2, but I want to point out that this is my gamma ray. Nuclear transformation is when one element changes into another through the bombardment of a particle. Okay, so when we take an alpha particle and we combine it with an aluminum nucleus, we get phosphorus plus a neutron. Using nuclear transformation has led to the extension of the periodic table. So all those elements in like 116, 117, all those have been made using nuclear transformation, where you're bombarding elements together to hopefully fuse together those nuclei. In order to detect radioactivity or radiation, we use an instrument called the Geiger counter. And what the Geiger counter does is it measures the amount of radiation being emitted by a certain specimen. Nuclear energy, well, there's two types. Fusion is when you combine two light nuclei to form a heavier nucleus. And this is what the sun does. The sun takes hydrogen and combines them together to make helium. Okay? And in the process of doing that, it releases an enormous amount of energy, plus neutrons. The second type is called fission. And fission is when we split nuclei into nuclei that are smaller and obviously weigh less. And nuclear reactors and the atom bomb use this process. So when you take a heavy nucleus and you bombard it and it splits apart, it releases an enormous amount of energy in the process. And we can capture that and use it to power cities, so on and so forth, or make nuclear bombs. The application of radioactivity has to do with radioactive dating and half-lives. We could also use it in medicine for radio tracers to produce images. We use radioactivity in nuclear power plants. And there's also obviously some dangers. So radiation is a form of energy that can be very dangerous and poisonous to your health. It can cause mutation and lead to cancer. There's alpha radiation, which can burn your skin. There's beta radiation, which can burn your skin, and gamma ray radiation, which can go right through your body and cause an enormous amount of damage.